All right, welcome. Let's do this. Let's talk about 4.1. Let me get on the right page first. There I am, 4.1. Nah, this is a black paper. Polynomial functions. This is a good chapter. This is one of my favorite chapters. Determine the roots of polynomial equations, apply fundamental theorem of algebra. Fundamental theorem of algebra. Sounds like a big deal. And of course, the emphasis will be upon the fun part. Thank you. Thank you very much. Determine roots of polynomials and apply the fundamental theorem. Roots of polynomials. Roots of polynomials is where a polynomial becomes equal to 0. Solving equations is kind of the essence of what math is about. Being able to take some real-world thing, express it mathematically, solve it, and then take it back to the real-world thing. What kind of a beam do I need to put in to support this kind of a load? There are equations that will measure the length and the weight that's supposed to be on there and determine what kind of a beam needs to go across a certain span. That's the kind of real-world kind of equation solving stuff that engineers, architects do all the time. So the idea of being able to solve an equation is fundamental to the concepts that we're going to talk about in here. All right, don't write this down, but just look at this. This is kind of a generic polynomial. A sub 0 x to the n plus a sub 1 x to the n minus 1 plus a sub 2 times x to the n minus 2 plus so on and so on, all the way down to, at the end here, a sub n. And notice that a sub n at the end has no variable with it. It's just a sub n. It doesn't have an x. This is what's referred to as an expression in one variable, meaning there's only really one variable in that. Now you're looking at this and saying, well, that's a variable, but those represent some number as opposed to the variable x. And so a sub 1, a sub 0, a sub 1, a sub 2, those are just simply, of course, different values for some number in there. So in this problem, it might be something like this, right? 3x to the third minus 7x squared plus 13x minus 5. That's a polynomial. We know what polynomials look like. We've been doing stuff with polynomials for a long, long time. So a little bit of vocab here. What are the numbers out front called? Coefficients, yep. And usually we're going to deal with them as integers, but not always. They could be fractions. But a lot of the times when you have a polynomial, those are often integers. But so let me back up here a second. So in this case, a sub 1 is 3, and a sub 2 is negative 7, and a sub 3 is a sub 0, 1, 2, and then this last term is negative 5. A sub 0 can't be 0. How come? Yeah, I think of what you're saying. A sub 0 can't be 0 because if a sub 0 is 0, then a sub 0 is an a sub 0. I know that didn't make sense. The first term can't have a leading coefficient of 0 because then this whole first term would go away, and then this would become the first term, and that would be a sub 0. So the first term has to have a coefficient that's not 0. Other terms could have a 0, like this guy. So the coefficient for x to the 6th power is 0. The coefficient for x to the 5th power is 0. The coefficient for x to the 4th power is 0, etc., etc., etc. So some of them can be 0, just not the first one. All the rest could be, just not the first one. Then you don't have that polynomial. So the degree of a polynomial is always the degree of the leading term. Now, by the way, remember the concept of descending order. Look at this as n. This is n minus 1, n minus 2. So the powers are going down 1 every single time. The degree of the polynomial is always the degree of that leading term. It's the highest power on the variable. And that's the thing that kind of tells you stuff about like end behavior, right? We've talked about that. Gives you an idea about the shape of the graph. So this is all stuff we kind of sort of know. We're just putting a little more vocabulary to it. And we are always going to deal with these as being positive integers. The powers. By the way, what's it mean if you have 3x to the negative fourth power? What's the negative do to the x? Puts it in the denominator, yeah. Yes, ma'am. Oops. X to the fourth.
Will you ever have an n that's 0?
Technically, this guy has an x to the 0 power down here. X to the 0 is 1, and so technically, yes. You never write it, though. Roman numeral 2. Remember complex numbers? Ooh. We did them back in Algebra 2 a little bit. And they kind of slide it in here, kind of coming from an assumption that you kind of sort of remember it. We are, for a little while, going to use complex numbers. When you get the square root of a negative, we're going to use I for a while. And then, and I'll be clear about it with you, then we're going to stop. So we do it for a little while. We're going to expand our number system out of real numbers into complex number system. But when we're done with that, I'll let you know. I'll say stop doing that from now on. And we'll get back to just normal number system. So let's remind ourselves about the complex numbers. So this is a quick review of Algebra 2, where you probably spent 2 weeks doing this last year. If I take the square, x squared equals negative 1, take the square root of both sides, I get positive negative square root of negative 1. Square root means you have to be able to take a number and multiply it by itself to get that. Well, so I could have negative 1 times negative 1, but negative times a negative is a positive. And of course, positive 1 times positive 1 is a positive. So how do I get the negative there? So, being clever, like they are, mathematicians created a new number system. Just like fractions kind of were a new number system, right? It used to be you just had a cow or you didn't have a cow. Well, sometimes one person killed a cow and some people get half and one other person get, So numbers are simply created to solve a purpose. And there actually is a purpose. There are practical applications for negative numbers, or negative square roots for I. Electrical engineering is one of those areas that uses complex numbers in some of their calculations. Way beyond where we are right now, but understand it's out there. It's not just fun math. And it is fun. But it has a purpose. So, by definition, the square root of negative 1 is I, which we call an imaginary number, which is no more imaginary than the number 2 is imaginary. It just represents something. Know this definition. Know that definition. You need to make sure you have that down. So, if the square root of negative 1 is I, then I squared, square root of negative 1 times negative 1, is negative 1. That's going to come up a ton. Have that in your head. I squared is negative 1. Comes up again and again and again and again and again, and then sometimes one more time. After. Again and again and again. Sound familiar? Kind of like, oh yeah, been there, done that. I'm hoping a little bit. So this is I is an imaginary number, but when you combine it with a real number, then you get a complex number. So a plus bi is a complex number. And what that has is two parts to it. There's a real number part, there's an imaginary number part. The real number part is the a out front, the imaginary part is the bi. Together, we call it a complex number. A plus bi, 2 plus 3i. That's a complex number. Now, just real quickly, my little bit of understanding about the electrical engineering idea is that a lot of times what they'll do in electrical engineering is they'll call that a variable. They'll say, okay, let's let this complex number be W. The advantage of that for the calculations that you do in electrical engineering is this one variable, where'd it go? There it is. This one variable carries two pieces of information. And so it allows them to do some calculations that they couldn't do without the two pieces of information coming along. Quick reminder, multiply. What's the next word that's going to come out of my mouth? We need to FOIL. Go for it. See what you get. First outer inner last. And the last, by the way, 3i times 2i gets you 6i squared. And the I squared, of course, becomes negative 1. And so that negative 6 becomes positive 6. 14 plus 8i. Grab your calculator. And on your calculator, you should see there's an I button, which I think is above the decimal point. Do the same calculation on your calculator. So that's kind of a nice deal. And for a lot of stuff that we do, I don't need to see this kind of calculation anymore. One of the things that you'll find as we advance through the math together is there's stuff I'm going to require you to do for a while, and then I'm going to show you how to do it on the calculator, and I'm all good with that. As long as we understand the process and the logic behind what's going on, let's find that it becomes more and more about being able to get an answer and not run through all the multiple steps that sometimes are required. Conjugates. That's a J, for those of you who have issues reading cursive. Conjugates. When you multiply conjugates together, fun stuff happens. Remember, the emphasis on this one is about the fun. Fun stuff happens when you multiply conjugates together. Conjugates are in that form, a plus bi, a minus bi. Put a box around that vocabulary and little stars and arrows, because we will use that vocab a little bit this year. So for example, if a plus bi and a minus bi are conjugates, multiply these two things together and have an aha moment. So when we multiply these things, the aha moment is all the I stuff goes away. And we're going to use that fact to do some things with complex numbers. All the I's go away when you multiply conjugates together. And you get a real number. Oops, sorry. You get a real number. Just 13 in this case. Okay. So is this a difference of two squares idea? Yes-ish. But look at this polynomial. This is a difference of two squares. 4x squared minus 9, back in Algebra 1, you spent a long time factoring difference of squares, and you got 2x plus 3, 2x minus 3. And the middle terms cancel out when you FOIL those together, which is why there's just two terms up here, because the middle terms down here end up canceling each other out. But what happens if I've got 4x squared plus 9? Well, back in Algebra 1 and Algebra 2 days, you would say that doesn't factor. But in the complex number system, it does. And it factors like that. Because they're conjugates of each other. So yes, it's in that same kind of mold of difference of two squares, but this is a sum of two squares now can factor in the exact same way, but to get that last term to be positive, you got to have an I in there. Because otherwise, a negative times a negative, or it just, you can't, to get this positive value here, you can't have one plus and one minus. But this gets you the other minus, which makes it come positive then. So sure enough, multiplying that out, middle terms still go away. Negative 6i plus 6i, those are gone. I squared, of course, is negative 1. So the 9 here is going to become plus 9. We're going to use that idea to be able to find complex zeros or roots of a polynomial. Remember, that was kind of our overall goal, was to find the roots or the zeros of polynomials. So yay, middle terms go away. So now, given that pattern, we should be able to glance at something like this, and in the complex number system, be able to factor that as x plus yi and x minus yi, the conjugates. Yep. Again, for a little while, we're going to do this with complex numbers. It'll go away again. Come second semester, we won't. If you saw something like that, you would say, nope, done, doesn't factor. But for a little while, we're going to kind of think in this mode. Yeah, okay, so even if there was a 25 there, then the 5s would break up. I don't know why I have so many examples of that. Yeah. Very good. Yes?
Would it matter if you switch the x and the y's? So if you have, like, y minus x.
You mean just this?
Yeah.
Nah, then you're just going to have... The I will be with the... you could have the I with the x if you wanted to. Either way. Because this essentially is the exact same thing, just turned around from the other one. All right. Got it. All right, so Roman numeral 3. I had way too many examples of that. How do you find roots? First of all, a root of a polynomial. A root of a polynomial is where the polynomial becomes equal to 0. It's not plugging 0 in. It's what do you have to plug in to get 0. The goal is to get 0 as an answer. The root of the polynomial is the number that you have to plug in to get an answer of 0. It's not plugging 0 in. What are you finding when you plug 0 into a polynomial? Yes, the y-intercept. You plug 0 for x in, you get the y-intercept. When I set this thing equal to 0, what am I finding? The x-intercepts. That's what the roots of a polynomial are, the x-intercepts. Graphically, that's what you're looking for. Where does this thing cross the x-axis? The roots of the polynomial are the x-intercepts. So I'm kind of the belief that everything I've said so far is somewhere in the back of your brain from last year. I don't think I've said anything new yet. If I said, here's this polynomial, find the roots, you would take it, set it equal to 0, and 95% of the time, you're going to factor. And so I take this polynomial, I got to be able to factor it, take the two factors, set them equal to 0, and solve. You're going to hear this phrase, zero product property. If I got two things multiplied together, the answer is 0. Product means multiply. If you got a product of some things and the answer is 0, somebody's got to be 0. You set each one equal to 0, right? And you solve. Yeah, Daniel?
Why is it minus x minus 1?
I don't know. Child to get positive 5.
Is this where are you supposed to multiply the 2 by the 5? And then
No, don't do that. That's a trick. Don't do that trick. It's a bad trick. It sets you up. It's just playing around with it. What are the options for 2x squared? 2x and x. What are the options for 5? 1 and 5. Look what happens when I FOIL them. That's 5x, and that's 2x, and minus 5x, and minus 2x gets me minus 7x in the middle. So I would much prefer you to do a little bit of guess and check. Now it's intelligent guess and checking. To get to to figure out what I wanted to use here for 2, I didn't use 5 and 12. Pick two random numbers. There's only one option for 2. 1 times 2. There's only one option for 5. 1 times 5. Figure out which combination will get you 7 in the middle. There is a trick that I've been trying to convince our junior high teachers to stop teaching, because it screws people up. Because they get up here and they do it wrong all the time. So the roots of this polynomial are 5 halves and 1. That's where this graph crosses the x-axis. So far, so good? Nobody blowing up? All right. Just kind of overkill here. If y, even a simple polynomial, y equals x minus 4, roots of the polynomial, what do you have to plug in to get an answer of 0? Set the polynomial equal to 0, solve. And sure enough, I cross at 4. All right? You don't need that example, probably. Just watch. You don't need to write all these down. Find the roots. What do I do? Set it equal to 0. Actually, this might be a good one to write down. So I got to get positive 4 at the end. Well, my options for positive 4 are 1 times 4 and 2 times 2. But I also need to be able to get a 3 in the middle. 1 and 4 should work, right? Because 4 minus 1 is 3. But the signs don't work. Because I got to get positive 4 at the end. So I can't have positive 4 and negative 1. That would get me 3 in the middle, but that wouldn't get me positive 4 at the end. We break out our trusted friend. We do know this, right? Do we need to sing the song?
Please don't.
X is equal to, how does it go? X equals opposite plus I square root all over 2a. There it is. Knew it was in there somewhere. Know this formula. And if you write it wrong, I will ding you for it. Notice what's going on right here. That line goes all the way under b. It's not just underneath the square root part. Write it correctly, or what you've written is wrong. All over 2a. So let's plug that into this and see what we get. There's my a, there's my b, there's my c. Wacka, wacka, wacka. Opposite of b plus or minus square root of b squared minus 4. 4 times a times c all over 2 times a. And what do we notice? Ding, ding, ding. I'm going to get a negative. So now remember what the roots are. The roots of a polynomial are where this polynomial crosses the x-axis. So what do you think this is telling me about where this graph crosses the x-axis? It doesn't. There are no x-intercepts. Now, there are zeros roots of this polynomial in the complex number system, but complex numbers aren't on the x-axis anywhere. So when I say the roots of the polynomial are where it crosses the x-axis, that really only applies to the real number system. So when we come up with a complex number as a root, it's not touching the x-axis anywhere. Okay? Yes. Or no. It depends. See what the question is. So if we wanted to continue this on a little bit, you could write it in that form. It kind of depends on what's going on. This question was just kind of like, what are the roots? Well, that's so. But here they are in complex number system. Then that's what x is equal to. Yep. So when I write it in a plus bi form, a and b are kind of their standalone numbers. So this is just negative 3 divided by 2. That's where that comes from. And then the negative inside here becomes I. So negative square root of 7 becomes I times the square root of 7. And that's over 2. And I just pull this part out front then. So, fundamental theorem of algebra. Every polynomial equation with degree greater than 0, and we're always going to use that, has at least one root in the complex number system. In other words, there's always an answer. When you set an equation equal to 0, a polynomial equal to 0, there will be an answer in the complex number system. Which is kind of a big deal. Because if you're trying to solve equations, this is saying there's an answer. Find it. Now, why that's a big deal, think about mathematicians in years gone by that didn't have a lot of technology available to them. They're doing a whole bunch of stuff by hand. And this is saying that if you keep at it long enough, you will find there is a solution to every single problem that you think of. It's got an answer. Maybe in the complex number system, but there's an answer. And then there's this corollary to the fundamental theorem, which basically says an nth degree polynomial has n roots. So if it's a fourth degree polynomial, you're going to have 4 answers. Some of them might be in the complex number system. Some of them could be just real numbers. Fifth degree polynomial, 5 answers. Third degree polynomial, guess how many?
3. Sorry, you said 5 earlier.
So close. I thought we understood what was going on. Yes, 3. Right. So, however many there are, that's how many you get. Don't make fun of her. So, hey. Yes, sir.
What would the roots be for 1 and for x?
So we're going to stay where we have positive powers. The fundamental theorem said you could have negative x, as long as they're positive. That's where we're going to stay. We're going to stay where we've got positive powers. So 1 over x would be x to the negative 1. Throw that out the window. So here's what we know. And you don't need to write this down. This is just kind of an intuitive thing. So an x to the first power, there'll be 1. I'm going to keep coming back, so be ready. There should be 1 root. And look, sure enough, this graph crosses the x-axis someplace once, right? A second degree polynomial. It crosses the axis in 2 places, therefore there's going to be 2 roots, and so on, and so on. Now, they don't always have to cross, right? So, look at this graph. Now, this crosses still, but look at what the other 2 roots are. They're going to be complex roots. So, you could get some real number roots and some complex roots together. So, if I were finding this in the complex number system, well, it's just 2 and 3. Right? If you graph this, if you find these factors, this would be x minus 3 and x plus 2. Set them equal to 0. You get 3 and negative 2. And sure enough, when you graph it, that's where it crosses the number system, or it crosses the x-axis. But where it gets more interesting is taking this idea and kind of turning it around. And that'll sometimes be a question. Now let me back up for just a second. Notice how these are the roots down here, and this is the polynomial. So the question I'm about to ask you takes that and turns the whole thing upside down. Whoops, didn't want to do that. Come like this. So if I take this whole thing, and we're going to group it together, and turn it upside down. So we're going to start with the zeros, the roots, and find the polynomial. Well, look what I do. Instead of saying x is equal to 3, I'm going to write it as x, bring 3 back over to the other side, write it as x minus 3. And instead of saying x equals negative 2, I'm going to bring the 2 back over onto the other side and write it as x plus 2. Now, you have to stand on your head to see this. If you're watching this on a computer, you can turn your computer upside down. But then, I'm going to take these 2 things and simply multiply them together, and that'll take me back to the polynomial. So, if I give you these roots, find the polynomial that has those roots. Well, if x equals 4, now listen to how this says, because I'm going to say this a bunch. If x equals 4 is a root, then x minus 4 is a, what's the word? It's a factor. There you go. And likewise, if x equals -1 is a root, then x plus 1 is a factor. And if those are the factors, you should be able to multiply them together to get the polynomial. And we do this to you all the time in math, right? We teach you how to do one direction, and then we turn right around and teach you how to undo that, right? You learned about squaring stuff, and then shortly after that, you learned about square rooting stuff, and multiplying and dividing, adding and subtracting, and so on. So polynomial, find the roots. Here's the roots, find the polynomial. Let me take a deep breath there. Anything? Questions, comments, thoughts? Yes, ma'am.
Do you ever have us look at a graph and then
Roots? If it's nice, yes. I mean, when I had this, looking at the graph, when I had this graph, you should be able to look at that graph and figure out kind of what the... Now, the thing that you got to be careful about is that polynomial has the exact same roots, but you got different y-intercepts and different things, so it's not the exact same equation. But usually the phrasing is find a polynomial that has, it's not the polynomial, because you can have multiple polynomials having the same roots. Okay? So find a polynomial that has these roots. So 2 and 1 plus 3i. Now here's the pay attention part, because this is a thing you didn't do last year, I'm thinking. Remember a minute ago when we did the quadratic formula and a whole bunch of you had a cow? Because we had to do the quadratic formula? Let's say the quadratic formula again. X is equal to the opposite of b plus or minus. So when I do the quadratic formula and I get a plus or minus in there, if the stuff underneath the square root is negative, that means I'm going to have a positive I thing, and I'm going to have a negative I thing. So as it turns out, if you have a complex root, 1 plus 3i, you will always have its conjugate as a root as well. So even if I don't tell you, you're supposed to go, aha! Ready? Aha! That was close. Okay. Because of the plus or minus. Because when I had the original polynomial and I found the factors, and then one of the factors was a quadratic that I had to plug into the quadratic formula, but when I did so, I got this plus or minus. So the answer ended up being 1 plus 3i, but there also would be a 1 minus 3i. So all on your own, and guaranteed I will do this to you. I will give you a polynomial. No, I'll ask you to find the polynomial where you know one of the complex roots. But if it's a complex root, its conjugate also occurs. Now that's not true with real numbers. I can just have a root of 2. Doesn't mean -2 is a root also. But if 1 plus 3i is a root, then we know for sure, because of that plus or minus in there, that 1 minus 3i is a root also. And that means this particular polynomial is at least x to the third power. There could be higher degrees. We're always going to go for the most simple. Don't just randomly throw other roots in. So yes, we're always going to go for the smallest one, but yeah, it would be an x to the third power. So when it was simple, easy numbers, that was real easy. But what I need to do here is to get myself into a place where I can find all the factors. So if x equals 1 plus 3i, then when I bring everything over, the plus 1 comes over as a minus 1, The plus 3i comes over as a minus 3i. The other root, 1 minus 3i. The 1 comes over as a minus, but the minus comes over as a plus. Notice that the only thing that's changing is the I part. Just the I part. So when I say x equals 1 plus 3i, I also have x equals 1 minus 3i. So when I bring everything over onto the same side, it's a minus 1 in both situations. The mistake that people make there is they change both of the signs. It's a plus bi, a minus bi. And so a word to the wise. I need to multiply all of that together. Always, 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 always multiply the conjugates together first. Because if you do that properly, anything that's got an I in it will go away. Now, nasty. I got 3 things times 3 things. I'm going to end up with 9 things. You're my go-to person on numbers. I'm going to end up with 9 things. But, again, if you do that properly, everything that's got an I should cancel out. So, I've got 3ix and, oh look, negative 3ix. I've got minus 3i and, oh look, positive 3i. And then at the very end, I got negative I squared, but I squared, of course, we know is negative 1, and so that negative 9i squared is going to become, eventually, a plus 9. So everything that's got an I should go away, and that's what I end up with. That polynomial. And then put the x minus 2, bless you, in with it. So you're just multiplying all 3 of them together. But if you don't do the i's together first, you're going to end up with nasty stuff. If you multiply these 2 things together, you could. It would be fine. It's just way harder. Now, if you want to check this, you whacked it all away and you came up with an x to the 3rd power. To check it, graph that thing. What would you expect to see? Yeah, but more specifically, what would I expect to see? Say again? Yeah, cubic. We got that figured out. And specifically, this one x-intercept would be at 2. And only one x-intercept. It's a cubic, so it might come up and then zigzag, but not touch, come back down and touch again. It might just go up and just curve a little bit. I don't know. So it could do, it could do something like this, where it would only cross at 2, like that. Or this graph might, it might just kind of come up across at 2 and just kind of do a zig without actually coming back down. I don't know. That's it.